Hello, welcome to video 18 in the lecture Advanced Mathematic Modeling. So in the last video we looked at the Bernoulli distribution and the geometric distribution, which was the waiting times for success in the Bernoulli in repeated Bernoulli trials. I showed you how to calculate the expectation value of the geometric distribution, and we learned some tricks. And today we want to see how we can calculate something like this with the generating function and how we obtain higher moments by the generating function. Okay, so, and you will see this goes very simple with the generating function. We don't need so many tricks, so we want to calculate the generating function f of function of s. And this was the expectation value of s to power k. So now for our distribution we can plug in the expectation value. So with this factor p we always can take out, and then we have here q to k minus 1 times s to power k, and we sum from k equal 1 to infinity. So now we use one of the tricks we had the last time. So here with k minus 1, here we have k. So we know how to write this a bit more simple. We have here p over q, and then we have q to power k, and so we have here q times s to power k. K goes from 1 to infinity. Now we would like this again to be a geometric series, but in this case we cannot just forget about the term k equal 1, because for k equal 1 this is not zero. So what we need to do, we rewrite this as first let's write here this p over q. Now we write here real geometric sum q, geometric series q times s to power k, and now we have here k 0 to infinity, but then we made a mistake and this we have to subtract again, and the value for k equals 0, something to power 0 is 1. And now we can apply here the geometric series. So we have p over q times the geometric series. Here is 1 minus q s. And then we still have to subtract here the 1. And then we can rewrite this as p over q. Then we have a big fraction here, 1 minus q times s over 1 minus qs. These ones cancel. For q we write again 1 minus p because we want to express everything in p. And then you see, if you work this out, this is p times s over 1 minus p s. And this is the generating function. Yeah. So the generating function is a similar calculation as we had before to calculate the first moment. It even was more simple because we didn't need to use this derivative trick. We could directly put it in a form where we have here the geometric series. So maybe have a look, how does this function look like? Again, we have s, f of s. This is a function which must go here to 1. And if you plot this function, of course it depends now on the probability p, the parameter p, but basically it's a function which looks like this. So again, the generating function is just a simple function of our argument s. And now we don't usually now need to look for the behavior at 0, because we know this already. We know already the coefficient or the probabilities of our of our series or probability function. We want to know the moment, so we have to look at the behavior of the derivatives of this function at point 1. So therefore this we now need to take derivatives. This may be cumbersome, but derivatives one can always calculate. Okay, when we have here fractions, you have to calculate a little bit, but it's possible. So d over ds of s, so you take here this, how it is called in English, quotient rule or whatever, and okay, you work with the derivative, and you can see, you can write it like this: p minus 1 times s plus 1 squared. And now if we take this derivative at position 1, then we have the expectation value is just this derivative at position 1. You plug in 1 for s, and you directly see this is p over p squared equals 1 over p. And this is the same result we got last video, calculating this per hand. Now you saw the more elegant calculation in terms of the generating function. So, and now, since we have the generating function, we can directly calculate higher moments. So first we need the next derivative, calculate the second derivative of f of s. Okay, it gets also here slightly more complicated, because when you take the derivative we get two terms, so it's 2 p minus 1 squared p times s over, so I made a shortcut in the video, I just wrote it down here, the derivative. And yeah, actually maybe I should say it again here, with all these calculations, always stop the video, try to do the calculations on your own first, and then look if you get the same result as me. If you didn't, maybe I made a mistake. Yeah? So okay, now we don't want to shorten this, but now we look at this at their position 1. So let's look at second derivative at position 1. So we have to plug in 1 for s, then this gets even more shorter, 2 p minus 1 squared p, and here we're left with p to power 3 minus 2 p minus 1 p over p to power squared. So, and we know that this here is the expectation value of x times x minus 1. Yeah? But actually we would rather like to have the variance. So what is the variance of x? And then we learned that this is that was the formula I gave you. That's the second derivative at the position 1, so this is this here, minus the first derivative, and then a plus, and then minus the first derivative at 1 squared. So now we take this here, so I again made a shortcut. So we have this here, and then we add the derivative, so that was the mean, and then we subtract the mean squared, so we have this expression, and then you put this all on the same denominator, and then you can shorten a lot. Magically this all simplifies, and we end up with 1 minus p over p. So that's the variance of the geometric distribution. And in p square. I mean, you see, like when you shorten here and you have take off this p, you have p square, you have p square, then you write here p over p square, and then you have something like 1 minus p over p square. So that's the variance of the geometric distribution. So the variance of our waiting time. And now if you we calculated this here, you see there's also the second moment, so which we directly also have here. Oh damn, so I saw again, sorry, sometimes this goes out of the window, but here I just repeated the formula, the result, so because this is important, so that's it's also useful in other contexts. And when you now have this result and this result, we can also obtain the second moment, so this is then 2 minus p over p squared. Okay, and in similar way we could now calculate higher moments if you take further derivatives. And so you see, with the generating function, may not be so simple directly to calculate the higher derivatives, but it's so straightforward here. Once you have this function, it's straightforward to calculate all the moments, and so we have only once to look for the convergence and something with the series, and then we're just in normal algebra, we just have to take derivatives. When you want to calculate the moments, then you have for every moment again to look for infinite sums. So it's much more simple to work with the generating functions. So what next? So I want to show you another interesting distribution which is related to Bernoulli. So you see, we had this very simple thing. We had the Bernoulli distribution, just this throw of a biased cone. Yeah? So that was very simple. Then we looked for the waiting time. So we had a sequence of Bernoulli trials, and we wait how long do we need to have a certain outcome. So then we ended up with the geometric distribution. And now what I want to do to change the question again slightly, we have again a sequence of throws of Bernoulli trials, but now the number of Bernoulli trials is fixed, but instead we want to know what's the probability that we have so and so many successes. So we come to the binomial distribution, which is also directly related to this, but in order to do this, I want first to make some remarks which we need at this position. The first remark goes to this formulas I gave you for the generating function, for the very general thing that the general sum of sequences gives the sum of generating function, and the product of generating functions gives the convolution. Let's apply this to probability distributions. What does these two theorems mean when we have a probability distribution? So the first theorem dealt with sums of sequences. So now applied to probability distribution, we have now the sum of random variables. Let's take only two, then you can generalize it directly to more. We have two random variables, x and y, and we assume they're independent. X and y are independent, and they have characteristic functions fx and characteristic function fy of s, and then the characteristic function of the sum then we want to know what's the characteristic function of x plus y, and then we have seen that this is just the characteristic function of x. Yeah, now comes the subtle moment, because like now you could think we just have to sum these s of x and this s of y, but the sum here would be totally wrong. Even though it looks like this at first glance, we sum sequences and then the generating function of the summed sequence is the sum of generating functions that we showed. But here we sum the random numbers, not the sequences. The sequences would be the probabilities to have the values dpi, and but this p, the probabilities for the outcome of a sum is not the sum of the probabilities. So actually you cannot apply this formula for the sum of random numbers, but only for a sum of distributions. So now, how can we relate this generating function of the sum to the generating functions of the independent variables? And now I write something down, which we come to this later when we have multivariate distributions. Let's say you have x and y are independent. Then the expectation value of a function g of x, h of y, here, so the product of this expectation value of this product can be written as the expectation value of g of x times the expectation value of h of y. And we come to this later when we look at multivariate distributions. But now if we use this here and we say, okay, we have independent variables, then we have here a product. This is expectation of s to y times s to x times s to y. And so we have such a product. And then we can write this as the expectation value of the first times the expectation value of the second. So we obtain a very important function, a theorem, the generating function of the sum of independent random variables This yields the product of the generating functions. So and this is often a trick in order to calculate generating functions. But then now we can still use what we had here before, because now we saw we have the product of generating functions. So this means then that the values in the distribution, the probabilities, must be a convolution. So we get a kind of lemma. We can write down that the sum, the new variable z, which is equal x plus y here, is given as a convolution. So the probability distribution of z equals the sum px of x times py of z minus x. And here we sum over all x. And this is a bit something to think about when you now apply these functions for the these theorems for generating function. You have to be very careful. What do you mean by a sum of these sequences? Do we mean a sum of the random variables, yeah, or do we mean the sum of generating functions, of the probabilities? So like the sum of random variables corresponds to a product, or even a convolution of probabilities. And whereas if you would have a new random variable where you add just the probabilities, then you would come to sum of generating functions. But then you see it cannot work. If you have a probability distribution, it's normalized to 1. So if you sum two probability distributions, it would not be normalized anymore. So the sum rule cannot directly be applied to discrete distributions. So with this rule, we can later directly write down the generating function for this binomial distribution. But first we maybe need to introduce some more ways to count events and this binomial binomials, and this we do in the next video, because this is already again 20 minutes. Okay, thanks for now.